Okay, well, maybe we can get started since we, are having a good audience. First of all, let me welcome on behalf of my colleague Chrysanthus Venaris and me, Dr. Fred Gardi, who's going to be giving today the seminar. So let me say a few words about him. First of all, I should mention that Dr. Gardi obtained his master's and PhD degree in 2001, 2005 in computer science, and this was at the ACE Marseille University in France. And then he also actually obtained his habilitation at the prestigious Sorbonne University, and this was with a thesis towards a mathematical programming solver based on local search. Habilitation, it means that you do a thesis beyond your PhD, and that then allows you to actually become a professor at a university. Now, it's mentioned that in his PhD thesis, Dr. Fred Gardi devoted his work on workforce and job scheduling, mixing algorithmics and graph theory. He's actually worked also on problems related to banking, especially real estate financing, planning. And then he's also focused his research from a more algorithmic point of view on local search techniques for combinatorial and mixed variable optimization and their integration in a general purpose model run optimization solver, which is called Hexaly, which we're going to be finding out today about that. The claim here is that Hexaly seeks to overcome the weaknesses that traditional tree search solvers have for solving mixed integer linear programming, like, for example, Cplex and Gorobi. And basically, Hexaly was initially named local solver because when it was first released in 2010, it was not at that time known as Hexaly, and now it is known as Hexaly Optimizer. Hexaly actually allows to solve immense combinatorial problems that otherwise with integer and constraint programming techniques can maybe take hours of computational time. I should mention that in 2022, in addition to the Hexaly solver, there's a different version. One is the Hexaly Studio that was launched as a low-code platform for mathematical optimization. And the goal of that platform is to expedite prototyping, development, and deployment of optimization applications, make it easier, and solve it, making it faster for data scientists and software developers to formulate models. The claim is saving 80% of the time and cost spent on optimization projects. So needless to say, we have a very unique and very novel software development that we wanted everybody to be aware of, our CAPD members, our graduate students and collaborators. And as you can see, the title of the presentation by Dr. Fred Gardi is Beyond MILP, Hexaly, a hybrid optimization solver. So Fred, welcome, and thank you very much for accepting to give this presentation. So it's all yours. Thank you.
Thank you. Thank you very much, Ignacio, for the introduction. Thank you for the invitation. Chrysanthus as well. Organization, Daniel, thank you very much. Thank you for this comprehensive intro. You said a lot. Thank you. Thank you very much. I will focus here on the last developments because you mentioned it. We started more than 15 years ago. And we started with the idea of building a solver exploiting local search for combinatorial optimization. It was the very first idea. How we can automate that through a model and run solver. So having a heuristic solver, it was assumed at the beginning. But with the vision, when we started commercially in 2012 to build a global optimization solver, hybridizing the main techniques you have in optimization, and also hybridizing the modeling paradigm you have, because this is really the core of my presentation. I will explain the tight link you have between the modeling and the solving, what you can do if you model better, I would say. So thank you again for the invitation. Now we are Hexaly, focusing on mathematical optimization fully. So developing this solver, Hexaly Optimizer. It's not a prototype anymore. It's not a heuristic solver anymore. It's used by a lot of companies now, 400 companies worldwide, and almost half of them are very big companies like Amazon, FedEx, Procter and Gamble, Starbucks, a number of manufacturing companies, because the solver is very strong on problems related to vehicle routing, scheduling, production scheduling, workforce scheduling, also packing, clustering, matching, assignment, location problems. All these discrete optimization problems are difficult to solve at scale in real life. We don't claim to be the best solver. It would be probably ridiculous to say that. For example, energy finance, you will see that today I will not talk too much about that. We are not bad, I would say, but we are not very differentiating today on some problems, yes, but not on large classes of problem. We don't claim that. On the problems I mentioned here, routing, scheduling, and beyond, so supply chain, transportation, manufacturing, the solver is very solid today, very solid. Also because we invest a lot in R&D. We have 60 people overall, 50 in R&D working on the solver. We really want to become the number one in this market and domain. We're really engaged. It's a passion. You can say, Ignacio say that I'm passionate for a long time about mathematical optimization. It's a passion, and I would say it's our vision. We really want to help the community to democratize mathematical optimization, and we think that it's also through a better solver, easier to use, that will succeed in doing so. So yeah, now I'm based in the US. We discussed that just a few minutes ago before starting. I relocated 22. We have this office in Brooklyn, New York, but a big part of the team still in Paris, in France. So here you have an overview of the clients we have. So a lot in Europe, of course, since we are you see that here, you hear that I originate from France. So Europe, a lot of clients there, but in the US, Canada, Latin America, also Japan, we have quite a number now and big ones. Because again, what we want with Hexaly is to be able to solve really real life problems at scale and with the full complexity of the business. This is what we want to do. So you gave a few words about Hexaly. The core product is the optimizer. We have other companion products. So we have this modeler, the studio, and the cloud. I will not detail that today. I will focus on the optimizer. This is what is interesting for you. Just to mention it, it's fully free for academia. So for students, professors, researchers, you can use it. You can use all the products, the optimizer for benchmarking for your class. The studio may be of interest for students since it's web-based. You have no installation. But again, I will focus on the optimizer today, explaining what it is, exactly this hybrid solver. So when you look at Hexaly, it's like any other solver. It's not. Sometimes people think it's a language. It's a mathematical language in some sense, but it's implemented through the API. But it's a software library, and it's accessible in all languages: Python, Java, C#, C++, Hexaly Modeler, which is our own programming and modeling language. But yeah, you can access it through Python. And at the first glance, when you look at Hexaly, you use it. It's really like Gardi, Cplex, or some of the solvers. You give a model, you write a model, you load a model, a mathematical model, you solve it, you launch the solve method, and then you get solutions. Infeasible solution, feasible solution. You get bounds. We support multi-objectives for all objectives. You have values for the primal. You have dual values, so bounds, lower bounds, or upper bounds, depending on the direction of the objective. You have optimality gaps. And you may have optimality proofs, inconsistency proofs in some cases, like Gardi. There is no guarantee, of course, but Hexaly is able to derive this information, so bounds and proofs. What is really different with Hexaly? It's different at two levels: modeling and solving. And modeling is an enabler for the solving layer. Uh, and it was built very hybrid at the modeling level and at the solving level. This is the idea I want to bring today on the table, but these ideas are not new. John Hooker in 2007 said that in a paper, in a short paper in Constraint Programming Letters. He talked about the future of constraint programming and more generally operational research. So good and bad futures. And he mentioned that. And at that time, when I read that, it struck me. Uh, I was both a researcher and practitioner. I have a foot in academia, but also a foot in industry, solving problems for some years. And when I saw that, I say, yeah, I think this is exactly what we need to build as a community, and maybe myself, if I can. You can see here, the key point is that modeling is a master and computation is a servant. No computational method should presume to have its own solver. So it means that should not be just CP solvers, MIP solvers, SAT solvers. All of these techniques should be available in a single system to solve the model at hand. And should combine to exploit problem structure. Any and exact methods should evolve gracefully into inexact heuristic methods as you scale. And this is exactly with this vision that we have started Hexaly, moving from the heuristic solver we had local solver based on local search to a global solver, hybrid solver, and this is exactly what Hexaly is today. It's a work in progress. We have a lot of things to do. A lot of things remain, of course. I mentioned for energy finance, where you have more mixed problem with continuous sub-problem, continuous domain that are sometimes non-linear, and it's more difficult for us today for Hexaly, but it's really what is guiding us as a vision. So Hexaly Optimizer at the modeling level, it's very broad interface, modeling interface. Again, accessible in Python. It mixes and unifies different modeling paradigms. So mixed integer programming, this is the mainstream, we all know, but also nonlinear programming, constraint programming, black box optimization, and multi-objective optimization. And in addition to that, because it's not limited to what was existing, we have added some new concepts, CP inspired, I would say, constraint programming inspired. For combinatorial modeling, we have introduced what we call sets and lists. Lists are the name for permutations inside Hexaly. We have introduced this new concept. These concepts are really new, I would say, as an interface, modeling interface of mathematical optimization solvers. Interval, optional intervals, it's not totally new. It's slightly different from what you have in constraint programming solvers, what you have in Hexaly, but these concepts are not new. They were present for 10 years in CP solvers, so CP optimizer from Cplex, now CPSAT or our tools. But we have added some concepts, especially optional intervals. And we have these very unique operators that can operate on these discrete structure. So it's what we call map reduce operators operating on collections, variadic collections. So it's collection that have a dynamic number of elements that can change during the solve. We have lambda functions, and we have global combinatorial operators that looks like global constraints in constraint programming, but again, it's slightly different. I would detail all of that. It's a bit abstract here, but just to mention that Hexaly is not just a mix of what was existing, but we have added some concepts, and these concepts you will see are critical to solve the problems we say we are able now to solve very efficiently at scale. And in the back end, so at the solving level, having these higher modeling structures, especially the ones I just mentioned here, the CP-inspired for combinatorial modeling, it's more structure, it's more mathematical properties we have. It's higher level models, and we can take advantage of that. We can take advantage of the structure, and we can leverage more of the state of the art than with traditional MILP or even CP solvers. MILP, if you look closer, the modeling is very low level. Binary modeling, just binaries, integers sometimes, but mainly binaries with linked by linear inequalities. It's very low level, and it's difficult to get the structure you have. So thanks to the modeling concepts we have introduced, we have more structure. We have this structure. And so we can leverage much more, especially I will detail that a bit today. We can leverage techniques related to column generation, branch cut price, decision diagram, column elimination. So all these techniques are based on reformulation. We can do that inside Hexaly, out of the box. The users have nothing to do. We can do that automatically. And so it's automated, auto-tune. And so it's really powerful to bring that capabilities to data scientists, for example, that are not really expert and that are not able in industry to implement such techniques that are very sophisticated. So you can see that we have almost all techniques from all the categories. So we have techniques from LP, QP, NLP, domain, MILP, MINLP, CP, SAT, LS for local search, heuristics at large, BCP for branch cut price, decision diagram, BBO for black box optimization because we support black box optimization. So a lot of techniques combined, tightly combined. It's not a portfolio solver. It's not just, okay, I have a model. I select among all these boxes, which is the right one. When you launch Hexaly on a problem, a number of these boxes are activated and collaborate. It's not just one. It's not all on all problems, but it's a large number of these ones. I will explain that just after. So the decision diagram techniques and column elimination, I know you know at Carnegie Mellon, you have a number of people that work actively on that, and we thank these people as we thank all of you for the great research we have done, because a number of the research that you've done, Ignacio, Santos, all of you working on MINLP, it's part of Hexaly, decision diagram, branch cut price, it's part of Hexaly. The last one, so decision diagram was introduced in 25, so it's quite recent. It's also to show that we really follow the trend. We really are at the forefront of the research now. In the version 14.0, we have introduced these techniques in complement of branch cut price techniques because they have the advantage to scale better, to maybe not close the gap, but to provide good bounds on a number of problems, especially routing problem at larger scale. So yeah, I will give a few details about what we do in different areas. So mixed integer nonlinear optimization. I will take this example, with a very simple example, to illustrate what Hexaly can solve and can model and solve. What you can model with Hexaly. So here, nonlinear modeling, what you can do. Here we have a very toy problem, but it's good to explain things. So we want to build a bucket. Here we have a surface of metal. but we will transform a 2D surface. It's a disk. We can say, okay, we have a disk of metal. We transform it into a volume, a 3D bucket, and given the surface we have, we want to maximize the volume of the bucket. It's an exercise in mathematics I found in a book. I give you here the geometry of the bucket. So you can see here the three parameters to decide the small radius, the large radius, V8. You have the equations that link the volume, the surface to these three parameters, these three variables. And you want to write the optimization model to solve the problem. Okay, you can do that with Hexaly. Again, it's very small, simple example, but it's good to illustrate how it works. First, in terms of modeling, so you declare the three decisions to decide, the three variables. Here they are numerical, real variables. It's what we call float variables. In Hexaly, I put some large upper bound here, so we can do better maybe, but okay, I say, okay, it's between 0 and I would say infinity. The surface is expressed very directly. Here it's written using Hexaly modeler, which is very concise for mathematical modeling, but in Python, it would be almost equivalent. It would be almost the same. So the surface is expressed directly from the equations I gave. You can see that the equation here, it's written as this. I want the surface to be lower than pi here because I consider to have an input some disk of radius 1. So the surface of the disk is pi. Then I maximize the volume. So I express the volume here directly, direct translation of the equation. I maximize the volume. I have everything. I can launch Hexaly. It's very simple. You just have 3 decisions, 5 variables overall. Very simple. You have optimality proof in less than a second here. So it's numerical. So here you have a gap of 0.01. You can choose the precision. Here we have the precision by default, 10 minus 4. But if you look at the problem here, so it's not a MINLP, but it's an NLP in the sense that the surface is quadratic and you can show that it's convex, but the volume is not convex. It's not convex here. And as you know, just a few years ago, the big solvers, MILP, MIQP solvers, were not able to take this kind of problems as an input. I think Cplex, but has not evolved since this now for years, is still not able to take that in input. And this is really what we want to bring with Hexaly. To industrial users, you want to bring simplicity in terms of modeling. People in industry, they don't want to have to understand, I would say, and to know about, is the problem linear, non-linear? Is it convex, non-convex? Is it smooth, non-smooth? Do I need to give first derivatives, Asian? No, they can't do that, especially data scientists. No offense for data scientists. You know what I mean? We have some people now in industry that engage in operation research project, optimization projects. Sometimes they don't have a background, formal background in operation research. And I think it's good. It shows that the technology, the domain is democratizing, and this is very good. And I think that we need to follow this trend and to offer tools that make the modeling much easier for people that are not top expert in the domain. And this is exactly what we want to offer with Hexaly. So here, what are the techniques at play on NLP, MINLP? These are the traditional techniques. Here, I would say that there is a lot of engineering behind the solver, but we really rely on the state of the art. I would say that we are at the forefront of the research, but we doesn't exceed the research on that. We inspire from the work, the top work in the domain, and you did at Carnegie Mellon, Ignacio, the team, MINLP, you know, so spatial branch and bound, cutting planes, mixed with some I would say, CP techniques. How about constraint propagation, filtering, all of that? So it's not new. The relaxation are solved by the simplex, the tunnel point, or augmented Lagrangian techniques. Again, it's not new, but a lot of engineering to make it faster and faster, more robust. Um, uh, I would not detail that here because you know that perfectly. So for computing global bounds, because we compute only global, we don't have local optimality like in some NLP solvers. We really focus on global optimality. So we have the techniques based on spatial branch and bound, outer approximation of nonlinear constraints to compute bounds. Uh, so depending on the nature of the constraints, we may have linear relaxation or convex quadratic relaxation, and they are solved uh, by simplex or interpoint methods or augmented Lagrangian, depending on the precise nature of the constraints and of the relaxation you have to solve. This is also where you have a lot of engineering. We'll not detail that because you know that perfectly. This is your specialty. Just a word on black box optimization before moving to the combinatorial stuff that I mentioned to be innovative. We support black box optimization, and you can imagine that, for example, on this model, the surface and the volume may be some functions that are not described analytically. You don't have them, or you don't want to describe them analytically. You have, for example, some simulation tools, numerical simulators to compute the values of the surface and the volume. You can do that with Hexaly. If you have that, you can just give the surface the volume as function, and this function refers to some codes. The codes will be called in a lazy fashion when the solver need to evaluate, and the functions that may be hidden behind are totally arbitrary. So it can be noisy, it can be non-smooth, as I mentioned. It can be also time-consuming function. So just one call to the function may be very, very long, so seconds or even minutes or hours. This is the case in numerical simulation with CFD, for example. So this is what I explained here. Black box functions may be anything. Monte Carlo simulation, discrete event simulation, agent-based, numerical. So CFD, for example, we have a number of clients doing that. Machine learning, you can have some forecast, I don't know, computed through a neural network. You want to plug the function directly in your code. You can also do high-level optimization. You want to have optimization calling another optimization model. Your optimization model, at some point, call another optimization model, high-level optimization. You can do that, and so the applications are known: stochastic, robust, high-level optimization, as just said. And here, if the functions are not time-consuming, you can use derivative-free methods, but if they are, you need to have surrogate modeling in place behind. So surrogate modeling, this is the idea of this function, which is dedicated, the evaluation is dedicated to a code, which is time-consuming. Each code is time-consuming. So I will try to reduce the number of codes to the black box. And for that, I will try to build a model, an analytical model of my black box. And for that, I use learning techniques, I would say. So I learn each new point that come. I try to refine the model I have of my hidden function. And once I have a model, an analytical model, so the problem become analytical, and I can use all the techniques I have in my bag for LP, QP, NLP, MINLP, combined with filtering, constraint propagation techniques. So it becomes MINLP, I would say. And we have the arsenal to solve that efficiently. We'll not dig too much into the detail. We have some mechanism to deal with exploration versus exploitation. So diversification, intensification, if you want to really cover the solution space, getting some points that are not fully located in the same region. You have a lot of engineering again to do here. This is what we have done, and it works quite well. Hexaly now is recognized to be a good black box optimization solver, especially when you have discrete variable. When we have discrete variable in addition to continuous, possibly, we make the difference with traditional solvers. Also, because we have, again, these derivative-free methods and all heuristics are at play here. Now, I arrived to I would say to the most interesting part here. So what makes Hexaly really innovative, I would say, compared to the research that have been done the last 50 years, and what makes it different from the solvers you have in the market. So it's these two concepts we have introduced. These are really two critical concepts that make Hexaly really different for discrete optimization. We have introduced some collection variables. We have introduced sets and lists. Set, if I define X as a set over a given parameter n, a constant n, for example, n equal 10, X will be defined by the solver. So the solver will decide the value of X, and the value of X is not atomic, not just one value, it's a collection of value. This is a first big difference. And so it's a subset of over 0 and minus 1 with the property that each value must be unique, but the size is variable. So the set can be empty. It can be, for example, 0, it can be 1, it can be 0, 1, 1, 0, 2. You can see that the domain is of exponential size here. And we capture the exponential nature of problems through these types of variable. The extension to take into account the ordering is a list. So Y is a list over N. It will be a permutation of a subset over 0 and minus 1. So here, Y, the value can be any permutation over any subset of a 0 and minus 1. Items are unique. What we call items are values, are elements. These are the 0, 1, 2, and minus 1. Variable size, but here it's ordered. So ordered means that it can be empty, it can be 0, it can be 1, it can be 1, 0, or 0, 1. It's different values. 1, 0, 2, 0, 1, 2. So order is different. Here's the order is taking into account, and you will see, you can imagine that it will be really helpful to express problems like routing or scheduling because the ordering is fundamental. If you have just these two concepts, it's not enough to really change the game in the modeling of the problems I just mentioned. So routing, scheduling, packing, clustering. You need to have the ability of apply operations on collection. In natively having a kind of map radius. For people in data science, they know map radius. This is this thing where if you have a collection, you can map each element of the collection. You can map it with a function. So you can apply a function to each element. And then you can compute something. You can aggregate. You can compute a function over the whole set. So this is this map reduce thing that data scientists know. So you can do that natively with the mathematical formalism you have with Hexaly API. So you can you can implement this combinatorial modeling here with Hexaly, which is really new. I don't know any other solver that offer that. And it's really critical to have the capabilities I will detail just after. So here, for example, to be concrete here, if you have this function to evaluate here in your model, in Hexaly model. So you have a set, and for each element of your set, so you don't know the size of the set, you don't know the elements that are in the set. The solver will decide that. You may have some constraints applied on that. It can be in objectives, whatever. You want to express that. So sum of the elements, so the elements to the power of 2 over the whole set. So here I took S as a set, directly a variable, but you can apply some transformation on S prior to do the sum of square. But you can express the sum of square over S just like this. So directly, naturally. So I want to sum e to the power of 2 over the whole set. Just this. And here you may recognize this symbol, which is the symbol to define lambda function in a number of programming language. So C#, Java, Python now, you have these concepts of lambda function, anonymous function you can declare on the fly to compute, to map some elements in collection. So we have took these concepts known in programming language, and we have put that into a mathematical modeling language. Modeling language at large, because it's accessible in Python here, in the mathematical modeling formalism. And it's really difficult to do. It took years to reach this level, to be able to support that as an API, because if you have a model with this expression, you have an expression tree here with that. It's like MINLP plus this thing. And so you need to support that in the back end. And it's really tough. But you will see that it's really powerful. I will take, again, a very simple example, maybe not as simple as the bucket. Here, this is a trade ring segment problem. You know it. So number of cities to visit. Each city must be visited once, and you want to minimize the total travel distance. This is a seminal problem in operation research. Yeah, no need to explain more. For the 50s, from the 50s, you have papers on many things, and especially on modeling the problem as a ILP, MILP, trying to have a better formulation, better relaxation, better something. And so the traditional approach is the seminal one by Danzig, Fulkerson, Johnson, 54, very well known because it's at the root of the branch and cut approach. One variable per edge, then you have the subtool elimination constraints to enumerate, or you don't want to enumerate, you can generate them on the fly. Again, that's the root of the branch and cut approach. So very well known, you learn that at school, at university. But you also have plenty of formulation based on flows. So single commodity flow, multi-commodity flows. You even have books that describe all this formulation and that analyze the strength and weakness of each formulation. So here, for example, Orman and Williams, you have a survey of different integral programming formulations for the TSP. But none of the formulation are close to the definition of the book. Here I gave one I found, so which is find a permutation of the cities that minimize this travel distance. So this function, which is, okay, I take the distance from the first point to the second, to the third, etc., and I look back. D may be a distance function, an arbitrary metric. It can be a distance matrix, whatever. You don't have that with MILP formulation, with the binary modeling, because binary imply lower level. You don't have the notion of permutation of anything. So, and this is exactly what you can write with the concepts I just exposed before. you can write the TSP. I would say finally we can write the TSP in a few lines as the book, the definition of the book. Through the list here, I use a list over n. N is the number of cities. I will index my city from 0 to n minus 1. So cities, it's a variable here of the problem of the model for Hexaly. It's a decision variable. It's a list over n. If you remember, a list may be empty. Basically, it's any permutation of any subset over 0 and minus 1. So I need first to say, okay, to the solver, I need to specify that here my list must be full. The permutation may be full. It's not a sub-permutation. It's a full permutation over 0 and minus 1. So for that, I can do it like this. I can say the cardinality of the list must be equal to n. I want to have all the cities visited. If this is a price collecting TSP, for example, you don't have to look to visit all the cities. You will not have this constraint, of course. But here, this is what you want, to visit all the cities. So here you write it like this. Again, it's very similar in Python or Java or C#. So you put it as the constraint here because you want this relation to be true. The count on the cities must be equal to n. And then I want to express the total distance. So I want to express this function especially, which is this thing here. I want to express it. So this is the sum of the distance from the first city in my tour to the second, then to the second, to the third, etc. You can write it directly like this. I can sum the distance from your city I minus 1. You will get the value, the index of the city, which is at the position I minus 1. And then I compute the city as position I get the distance. Here it's a distance matrix, but it can be an arbitrary distance function again. And I have the loop back here from the last city to the first one to close the loop. I minimize the objective. I can launch Hexaly. Here I'll launch on an instance from the TSP lib. Not so simple. Not so simple to solve. Here you have 443 cities. You will see on the next slide, it's not so simple. Hexaly is able to get solution and to prove the optimality on the solution that we get after a few seconds here. So what is at play behind that? I will pass this slide. It's the extension, how you extend this model to the CVRP, which is more interesting from an industrial point of view. You have all what you need to extend. Sorry, I'm late, so I will go straight to the what is happening behind. What is happening behind when you launch such models? When you launch models with collection, these collection-related operators, these collection concepts, we have especially, not only, but especially these two blocks that are at play, the exact techniques based on branch cut price decision diagram that are known to be state of the art if you want to have bounds, to have proofs on the routing, but also scheduling, packing. We have extended recently decision diagram techniques to scheduling. And heuristics. Heuristics are critical to get speed, to get scalability on these highly discrete problems. So here, of course, greedy grasp methods, but mostly local search. Local search. It was the very first idea we had when we started local solver 15 years ago. We wanted to have these techniques at play working as they are implemented in practice, not just some local search in branch and bound tree, but really local search working on structure like the collections we have here. And this is what you have behind. So these techniques, your BCP, DD, they use all the blocks here because it's raw formulation. We use some MILP, MINLP techniques, and we may use the dual. It may be MINLP or LP, and so all these blocks are may be used, not necessarily all, but at play you are all these blocks that are used, especially all the LP techniques for relaxation. And here, what is happening? I will give a benchmark and I will conclude on that. Here, we benchmark against Concord on the TSP. So it's a benchmark on the TSP problem, Concord, and we also benchmark against Gardi. Not to say Gardi is bad, but Gardi is recognized to be today the best MILP solver. So, okay, we want to show something here about that. So Concord is this is a state of the art. It delivers optimal solutions for instances until 1,000 cities. This is what we have here. There's a number of cities at the bottom, and we have optimal solution found. It may be in hours of computation on big machines. Here we will look at what is happening in 1 minute for Hexaly and Gardi. But so we compare to the state of the art. Concord is the state of the art. You know, the solver developed by Applegate, Bixby, Cook, very well known. It's based on branch and cut. And the point is that it's not just branch and cut. It's branch and cut plus local search. Especially they have added to get primal solutions very quickly. They rely on LKH, an implementation by Elsgone of lean Carnegie heuristics. A very optimized implementation, very fast. And so it's a combination of branch and cut, so dual methods, and primal heuristics, local search. And this is exactly what we have behind Hexaly here at play. This is the two blocks in orange, red here that are really difficult to activate if you just have a MILP formulation. And thanks to the list formulation, we can activate that. And this is why Hexaly here is able to deliver state-of-the-art solution, near optimal solution. And so you can keep on scaling here, but at some point in 1 minute, the results will degrade, especially the lower bound. Primal bounds, primal solutions may be still quite good because of the heuristics, but of course, there is no magic. We don't claim that we are able to scale infinitely like this. It's degrade, especially the bounds. But here it's what is interesting. If you just take Gardi, a branch cut price implemented with Gardi, we took the branch and price approach implemented by Gardi in their documentation. It's a decent implementation. It's not very sophisticated, but it's a decent one. It's just branch and cut. So there is no local search, just branch and cut. And you can see here that it's not scalable at all. You can see that, yeah, just 200, 300 cities, you have no solution found here. Because even if in our mind, Concord is branch and cut, and this is the power of branch and cut. It's not just branch and cut. It's branch and cut plus local search, and they play an important role here in scalability, in getting primal solutions very quickly. And so this is the power of the two, and this is what we have behind Hexaly here at play. But of course, it's not just on the TSP. We have implemented all the machinery so to be able to work on abstract mathematical models with lists, sets, all the operators are described. And so it's much more generic, but just the TSP. It works on Baker routing, scheduling as well, packing I mentioned. So if you want to explore the benchmarks, we have very factual benchmarks. Our intent is not to cheat here. It will be ridiculous because we offer trial to people. People can try it for free, so cheating would be really ridiculous. We have factual benchmarks on the website, hexaly.com/benchmarks. Again, it's factual and selected benchmarks. We acknowledge that. we don't pretend to be the best solver. We just want to show the difference Hexaly makes because of the introduction of these modeling concepts, coupled with the machinery, the algorithmic machinery we have behind, the difference it makes on concrete problems that are difficult to solve otherwise. Sorry, I'm 10 minutes late. Sorry for that. I will stop here, and I thank you very much for your attention. Thank you.
Well, thank you very much, Fred, for a very, very interesting and stimulating presentation. And again, well, we do have still time for questions. Let me start by maybe reading. There's a couple of questions on the chat, Fred. The first question by Sharab Shukla is the following: says, for the TSP problem and its variants, what does Hexaly do different from Gurobi or Cplex that helps it manage the combinatorial explosion better? So in other words, so what is Hexaly different from Gurobi and Cplex, in particular as applied to the TSP problem?
So when you formulate, for example, so I mentioned that here, what is considered to be the best formulation for the TSP is a formulation with subtotal elimination. So if you want to use this approach, you have to enumerate all the subtotal elimination constraints, which is exponential. So or if you don't do that, and you cannot do that in practice, you have to put in place a branch and cut approach, which is a use of MILP, but it's not a direct frontal model you solve. You need to implement yourself a branch and cut approach. So, for example, Gurobi is giving an implementation of that on their website. But again, branch and cut alone, it's not very scalable. This is what we show here. If you don't have local search methods coupled to these techniques that are dual techniques, branch and cut is a dual techniques mainly, you don't have very good performance, in fact. And Concord is the coupling of both techniques
Right.
at the best level. They have the best branch cut price for TSP, and they have the best local search for TSP combined. It's the best, the very best. And what we show here is that we don't beat Concord. Would be ridiculous to say that. They have really the best TSP solver, but to show that Hexaly kind of mimic the techniques you have behind Concord, so branch and cut here, plus local search. And this is something you don't have in traditional MILP solvers at play when you launch a model, whatever it is, with subtotal elimination constraints or a commodity flow model. These are not the techniques that are at play behind. Same for vehicle routing or for scheduling. And this is what we have. And in some sense, there is no magic. Sometimes people say, but it's kind of magic. Actually, do you rely on, I don't know, GPUs or quantum things? No. There is no magic. It's just that we have a solver where we have enabled some state-of-the-art techniques inside, thanks to this higher level modeling concepts that I explained.
Okay,
and this is a titling.
Maybe next question for Francos Benecos asking a question. In your opinion, how much of an improvement over commercial and open source solvers like Ruby or OR tools comes from the more flexible, richer modeling capability that you have in, with more sophisticated underlying methods?
So people today, I would say that even if the concepts we have introduced, so yes, it's an advantage. Hexaly is very expressive.
Right.
The way you express problems, you can express almost any problems. Now you have to solve them. And we don't claim we can solve at hand any problem in any time. No, but I would say that companies today, they don't buy it for the expressiveness. It's of a second order, I would say. It's interesting. You have easier model. It's easier to maintain. It's closer to the business reality. It's you don't have to linearize. It's the advantage of non-linear modeling. Combinatorial modeling, same. It's closer to the business requirements, but they buy it because it's much faster and much more scalable. They buy it because they solve problems they cannot solve with Gardi today.
I guess from a more mathematical point of view, there's also a question for MI-NLP problems. In which cases is Hexaly able to provide a global lower bound? In other words, can you guarantee that you can get rigorous lower bounds when you solve, unstructured MI-NLP problems?
We deliver global rigorous lower bound. So as I explained, we are not really interested in computing local on NLP, for example, to computing local optimal solutions. So we deliver global bounds, and the global bounds are computed through spatial branch and bound based on outer approximation. So again, it's really the state of the art. State of the art. It's the state of the research, cutting planes, RLT, cuts, of course, so McCormick, etc. So all this machinery that guaranteed to be outer and so to have rigorous bound.
Yeah, there's also a question if you've considered working to make Hexaly more compatible with algebraic modeling languages like Pyomo or maybe even GAMS. We have, presence from some of the GAMS people here. Is it possible to somehow use Pyomo or GAMS and for
So
Hexaly, or do you
the
have to?
blocker, the
Yeah,
blocker here is this part. You see, it's really this thing. We didn't want people to use Hexaly just through a subset of the modeling formalism we offer, um, knowing that the big advantage Hexaly offer is based on these concepts we have added. So today, Hexaly is really good, and most of our clients buy Hexaly for supply chain, logistic, manufacturing. So for solving routing problems, scheduling problems, packing problems, but routing and scheduling is, I would say, it's 80% of the clients. We have used it for one or both problems because it's so differentiating. It's so fast and scalable and flexible in comparison to all the other solvers. So if we embed into Pyomo or GAMS and people don't have these concepts, they would be surely deceived. Uh,
right.
because yeah, you have just access to a part which is um, which is interesting, and this is something we are discussing internally because on, for example, MINLP capabilities, now the solver is really strong. The last
Mm.
benchmarks we have internally, we will maybe publish things soon because we have things that are really, really interesting. So yeah, maybe we will do. We'll see. But yeah, we prefer to be conservative
Yeah.
until then.
Oh, yeah. Also, another quick question. Gurobi also uses heuristics under the hood, so to speak. And
Yeah, sure.
question is, are your heuristics different from theirs, or do you use them more aggressively? Can you make any comment on the use of heuristics?
I don't know precisely the heuristics they use, but they use two types of heuristics. Historically, the heuristics in MILP solvers, and that's why we developed local solver at first.
Right.
The heuristics were mostly based on relaxation.
Mm,
So it's heuristics inside the branch and mount tree or calling an LP and
right. Right.
solving it through simplex or interpolation. So it's relaxation-based heuristics. It's mainly the heuristics you had. Gurobi has innovated, and they have pushed, maybe because of us, I don't know, they have pushed what they call no-rel. No-rel heuristics is for no relaxation. It's
I see.
heuristics based on some techniques where they don't call relaxation, and so no LPs, which is appropriate on highly combinatorial problems. And but I don't know what are these heuristics precisely. I don't know if it is related to local search or whatever. What I know is that when you compare Gurobi to Hexaly on a number of problems, but mainly because you don't have the same modeling level, we
Right.
are at a higher level, more structure, we have much better results
Yeah. Maybe
on
next
the
week.
problems I mentioned here. Again, disclaimer, I don't claim we are better than Gurobi or anything.
Yeah, no, no, it's okay. Hey, Chrysanthus, maybe if you want to ask the next question since you posted on the chat. Chrysanthus, can you hear me?
Yeah, Ignacio. Yeah, I can take it live. Fred, first of all, thank you so much. Super interesting presentation, and I'm really looking forward to putting my hands on the solver at some point. So the question is, will he actually infer what type of problem is being asked to solve and then draw, the right tools from the bag.
Mhm.
And because there was no direct instruction, this is a TSP, right? It was just the permutation
Exactly.
constraint. And then my side question was, okay, if I'm not experienced, let's say, working with Hexaly modeling, right? Modeling in Hexaly. So what if I slightly deviate from this perfect formulation? It will still be a TSP model, but maybe Hexaly won't be able to detect it properly, right?
Exactly. But we don't try to detect a TSP. Not exactly that. So we have a pre-solve and a kind of orchestration layer. So first a pre-solve, and then an orchestration layer that coordinate all the techniques. We have some techniques that are more primal, some more dual. They exchange information during the resolution. But yeah, first, there is a static analysis of the problem, and yeah, we don't try to detect the TSP structure or the techniques that we have. For example, here in red, in orange, in red, so related to BCP, DD, local search, they really work on the structure I have introduced. And so you can do, I will not dig too much into the detail here, but you can do a lot on this abstract structure. So it will not be a TSP, it will be a list and with maybe a distance function expressed at some point. And so of course you have a phase of detection of the model. What is your model? What is the model composed of? What is the structure you have here? Trying to detect if you have special structure, we can maybe exploit more. We have some specific algorithms, or we can specialize, parameterize differently some blocks here, some techniques to be better, faster. For example, this is the case of interpoint methods. If we detect that the problem is convex, imagine you have a model which is continuous with some functions. And so we try to detect convexity. Is the model convex or not? If it is convex, we would parameterize IPM methods to be more efficient to take advantage of that. And this is the same with combinatorial modeling. If we detect some structure, some distance function that have some good properties, we can go faster. But always we have the basics that work on the model. And here it's a lot of engineering, and I would say it's a lot of feedback from the user. So we had some clients coming and say, oh, I have this VRP model with some, I don't know, driver brakes. Doesn't work very well. I put them. So first thing is, oh, the model, maybe here it's not the best way to model it. And because this is it also. The way you model, you may have yeah, some difference in performance. But the first work we have done is, okay, we try to be as fast on a given problem. Then if the formulation is not exactly the same, this is about preprocessing. Like Gardi does on MILP, you try to reformulate to have a much more appropriate structure. And so this is what we do on this big expression tree. This is not a matrix. This is a difference. It's not matrix oriented. It's an expression tree like in MINLP, but it's an expression tree with these additional concepts, combinatorial concepts on it. List, set, interval, set, collection, operator on collection, lambda function. And so you try to pre-process to recover things so it's a lot of engineering. But today, I think we have something which is ready to say, I'd like to try it on, for example, TSP or VLP. You can have pretty dirty models, really dirty models, real life, badly modeled things. And surprisingly, it works quite well on that domain. Scheduling, same. But yeah, there is a lot of engineering, especially in the pre-solve here.
Yeah, maybe we're already running a little bit beyond time, but
Yeah, sorry.
if I can ask you a very quick question, because I was very surprised on slide 13 on the optimal bucket problem, you were reporting 75,000 iterations, and if I read correctly, zero
Yeah,
second.
sorry. Yeah, it's here.
And yeah,
Yeah,
and slide 13, yeah. You have 75,000
yeah, yeah,
iterations,
yeah.
then you report 0 seconds. And then in slide 28, when you had a TSP problem with, I think it was 400 cities. It took 400 iterations. The computational time was 6 seconds. But it calls very much my attention to your very low CPU times. Can you comment? Are you doing anything special in terms of computing architecture that allows you to, do these computations much faster? Any special comments on that regard?
Uh, so we have good engineers in the team. So myself, I'm passionate by computer science, software engineering. I follow this trend, this training first. So yeah, there is a lot of low-level engineering things. Now, what you see here is the number of iterations is high because the latest iteration in Hexaly is very, very quick. So this is the one iteration is the granular step where you can interact with the solver through callbacks. And
Right.
we wanted to have callbacks callable at a very granular uh, step. And this is related to it's historical because of the derivative free methods, local search methods. They can do a lot of iterations.
Mm.
So in fact, all the solver is synchronized on these small iterations that are like not maybe 10, 100 milliseconds.
Nice.
In some case, depending on the size, the density of the model, etc. But so each iteration is very fast, and it's also technically it helps to dialogue with the solver through callbacks if you want. But yeah, there is a lot of engineering to take advantage of cache locality, for example.
All right. Okay.
The number of defaults of cache, this kind
Yeah.
of things, it has a big impact in terms of performance on modern architecture. We take care of that.
Okay, well, thank you so much. I think we already again exceeded the time limit. So let me again thank you so much for a very, very interesting presentation. And just to let the audience know, the presentation and the slides will be posted in the, CPD website if you're interested in that. And again, thank you so much for really. And again, everybody should be aware that academics can have free access.
Oh
So
yeah.
definitely be very interesting for us to try Hexaly solver. And by the way, I do have to give credit to Dr. Anna Robert from Total Energy. She's the one who actually brought to my attention Hexaly because I
Thank
didn't
you.
know anything about it. So we should really thank
I know Anna very
her
well.
for
Yeah,
that.
it's a
Yeah,
colleague
yeah,
of mine in France. Yeah, yeah,
yeah, yeah.
very
Okay.
kind to have mentioned Hexaly to you. Thank you again. Thank you, Ignacio. Thank you,
Okay.
Chrysanthos, for the invitation. Your kind comment about Hexaly. As you said, it's free. Just come with your academic email. You can get some license for free and use it. You also have technical support. So if you have trouble with Hexaly, you have questions, you have some bad results, just contact us. It would be really our pleasure to help. Thank you again. Thank you very much. Have a nice day and see
Well,
you.
thank you so much again.
Thank
Have
you.
a
Thank you. Bye.
nice day, and everybody, thanks for attending this very interesting talk. Thank you. Bye-bye.
Thank you. Bye.
Okay.